Alright, in this video we're going to take a look at a harder problem involving empirical and molecular formulas. It's called combustion analysis, and it's used for organic compounds, typically with carbon and hydrogen, and then possibly other elements, as in this case oxygen as well. So we're given a compound called vanillin, the dominant flavor in vanilla, and we're told it's made of three elements: carbon, hydrogen, and oxygen. So it's related to a hydrocarbon. We're going to do a combustion analysis to determine its formula. Now, what does that mean? Well, combustion analysis is exactly what it sounds like. We're going to take a sample and put it into a furnace. And in this furnace, we're going to burn the compound. So it's made of carbon, hydrogen, oxygen. We're going to burn it. To burn it, we add oxygen gas, just like a hydrocarbon combustion reaction. It's going to produce two products. If it burns completely, it will produce CO2 and water vapor. The gases that come out, the CO2 and water vapor, are passed through two other chambers where they are absorbed. Now I'm trying to remember, I think in the first chamber, the carbon dioxide gets absorbed first, and in the second chamber, water gets absorbed. I might have that backwards. I'm doing that off the top of my head. The absorption is done chemically, so there's a chemical in these chambers that absorbs the gas. For example, if we put, and I think I do have this backwards, if we put sodium hydroxide, for example, into one of the containers, it will absorb, in fact I do have this backwards, I think it absorbs water first and then CO2 second. So what we would do is put into the first container here something like an anhydrous form of a hydrated salt. So what happens is, as these gases, CO2 and water, and excess oxygen, remember we put oxygen in to burn it, as they pass through this chamber, which contains anhydrous salt, the anhydrous salt absorbs water. If we measure the mass of the salt before and after, we can figure out how many grams of water were produced in the combustion. What comes through the container is whatever CO2 was produced and whatever excess oxygen gas was produced, or was still there. The second container contains sodium hydroxide, and sodium hydroxide will absorb CO2, and then at the end, only excess oxygen comes through. So the oxygen goes in to burn the compound, excess oxygen is used, so some oxygen is left at the end. So what we do is, as we see in this problem, we measure the mass of the compound that we're burning. So in this case, 105 milligrams of vanillin was being burned. And then we measure the mass of the two products. So we measured 50.0 milligrams of water produced, and we measured 243 milligrams of carbon dioxide produced. From that information, we're somehow going to be able to go find the empirical formula of the compound. Now, how do we do that? The key is recognizing, when you look at that formula, it's made of carbon, hydrogen, and oxygen, that in the water, all of the hydrogen that ends up in the water came from our compound, right? H2O, where did that hydrogen come from? Well, it came from the vanillin. In the CO2, all of the carbon that's in the CO2 also came from the vanillin. So if we know how much water was produced, 50 milligrams, we should be able to somehow go back and find how much hydrogen was in the water, and therefore how much hydrogen was in the vanillin. Likewise, if we know how much carbon dioxide was produced, we should be able to find how much carbon was in the carbon dioxide and how much carbon was in the original vanillin compound. Now, why is oxygen problematic? Well, for two reasons. The first reason is that the oxygen ends up in both products. There's H2O and there's CO2, so oxygen ends up in both of those products. But the other problem is that the oxygen in those products didn't all come from our compound, because to burn the compound, we had to add O2. So some of the oxygen in the water and some of the oxygen in the CO2 came from the added oxygen that we used to burn the compound, so oxygen is going to provide a small problem for us. But let's jump in and see if we can begin. So we're going to start out by finding the millimoles, and I'm using millimoles because these masses are milligrams. If they were grams, then we would just find moles. So I'm going to find the millimoles of carbon and hydrogen in the compound. To do that, we'll take the mass of the CO2, so 243 milligrams of CO2, and the mass of the water, 50.0 milligrams of H2O, and we're going to use some unit multipliers to figure out the millimoles of carbon and millimoles of hydrogen that were in the compound. So here we go. The first thing we'll do is convert the milligrams of CO2 to millimoles of CO2. Now at first that's a little confusing, but think about this. If you know the ratio of moles to grams, that's the molar mass, it'll be the same ratio as the ratio of milligrams to moles, the same ratio. So for example, carbon's molar mass is 12.01 grams for every 1 mole. Then there must also be 12.01 milligrams for every 1 millimole of carbon. So this is the millimolar mass of CO2, which is the same as the molar mass of CO2. So I look up CO2 on my periodic table. There's 1 carbon and 2 oxygens. So 12.01 plus 2 times 16, 44.01 milligrams. Now if this really bothers you, then what you could have done is simply converted the milligrams to grams, then grams to moles. But I like leaving it like this because now my numbers are going to be larger and I think easier to work with. Now I'll get rid of the millimoles of CO2, and what I wanted to know was how many millimoles of carbon were in the compound. Looking at the formula of CO2, I recognize that for every 1 millimole of CO2, there are 2 millimoles of oxygen, CO2, and there's only 1 millimole of carbon. There's only 1 carbon in the formula for CO2. So on my calculator, 243 divided by 44.01, we get 5.52 millimoles of carbon. And I'm going to put a box around that because later we're going to use that number in one of our millimole ratios to find the empirical formula. Doing the same kind of calculation for water. We'll first get rid of the milligrams of water, and we'll convert that to millimoles of water using the millimolar mass of water. 1 millimole of water, 18.02 milligrams. There's 1 oxygen, that's 16, and 2 hydrogens, 2 times 1.01, so 18.02. So again, 1 mole of water weighs 18.02 grams, so 1 millimole of water weighs 18.02 milligrams. Now here, don't make a silly mistake. We're going to convert the millimoles of water to millimoles of H, hydrogen. And look at the formula for water. It's H2O. So for every 1 millimole of water, there are 2 millimoles of H. So 50 divided by 18.02 and times by 2, and we get a number very similar, which is nice, 5.55 millimoles of hydrogen. And again, I'm going to put a box around that because that's going to be useful later when I find my mole ratios, or my millimole ratios, to get the formula. So I've got 2 out of the 3 elements in this compound. How do we go and get the oxygen? Well, again, the problem with oxygen is that 2 problems. It shows up in both the CO2 and the water. And secondly, and even worse, the oxygen in the CO2 and in the water didn't all come from the compound. So we have a problem. What we're going to do is find the oxygen in an indirect way. Let's follow with me. I'm going to take the millimoles of carbon and hydrogen that I've got, and I'm going to go find the milligrams, the masses of carbon and hydrogen. So the milligrams. So 5.52 millimoles of carbon. If I convert millimoles to milligrams of carbon, that's the millimolar mass of carbon. So 1 millimole of carbon weighs 12.01 milligrams. Now this might seem a little strange. We're going back to milligrams, but notice we're going to milligrams of carbon, not milligrams of CO2 that we had originally. Do the same thing for the hydrogen. We had 5.55 millimoles of hydrogen. Convert the millimoles of hydrogen to milligrams of hydrogen. 1 millimole is 1.01 milligrams from the periodic table. And that's going to give me milligrams of hydrogen. So let's calculate 5.52 times 12.01. Gives me 66.3 milligrams of carbon, and 5.55 times 1.01 is 5.61 milligrams of hydrogen. If I add those together, I'll get the mass in milligrams of carbon and hydrogen in the compound. Remember, this carbon and hydrogen came from our compound. So let's add them up. So 66.3 plus 5.61, rounding off to 1 decimal place, is 71.9 milligrams of carbon and hydrogen. Now pause the video and see if you can figure out what I'm about to do next. We know the mass of carbon and hydrogen that was in our compound. We were trying to figure out how much oxygen is in the compound. Can you figure out what I'm going to do now? If you said I'm going to find the milligrams of oxygen in the compound, you've got it. Because remember, we were told in the original question that the compound had a mass of 105 milligrams. We burned a 105 milligram sample of the vanillin. And we know that there was 71.9 milligrams of carbon and hydrogen in that compound. And there's only one other element, oxygen. So can you see what we're about to do? If we take the mass of the compound, 105 milligrams of the compound, I'm going to just represent this as C, H, and O. The compound was made of those three elements. And we subtract 71.9 milligrams, which was carbon and hydrogen. What's going to be left is the milligrams of oxygen that were in the compound. So 105, take away 71.9, leaves me with 33. Now technically I should just say 33 because there's no decimal places in 105, but I'll keep one extra significant digit, 33.1 milligrams of oxygen. Now our goal in finding an empirical formula is to do mole ratios, or in this case millimole ratios. We already have 2 out of the 3 elements. We need the millimoles of oxygen, and we now have the milligrams of oxygen. So here we go. Go find your millimoles of oxygen that were in the compound. There were 33.1 milligrams of oxygen. Convert your milligrams to millimoles of oxygen, and we're going to be home free. So 1 millimole periodic table is 16.00 milligrams for oxygen, and that's going to give me 33.1 divided by 16, 2.07 millimoles of oxygen. And I'll put a box around that. So notice now in boxes we've got the millimoles of oxygen that were in our compound that was burned, the millimoles of hydrogen that were in the compound that was burned, and the millimoles of carbon. The oxygen was harder to find because, again, it ends up in both products, CO2 and water, and the oxygen in those compounds didn't entirely come from our compound. Some of it was oxygen that we added. So our way of finding oxygen was indirect. We found the millimoles of carbon and hydrogen directly from the CO2 and water, because all the carbon in the CO2 came from our compound. All the hydrogen in the water came from our compound. We converted those back to masses and subtracted that from the mass of the compound to get the mass of oxygen in the compound indirectly. And now we've got the millimoles of oxygen as well. So the last thing we need to do is go find millimole ratios. Pardon me. So millimole ratios, the same way we did with percent composition, but we're using millimoles instead of mole ratios, but it's the same idea. So we'll take the smallest number of millimoles. So in the three numbers that we had, the smallest number was oxygen. 2.07 is smallest of those three. So we'll divide the others by the smallest number. So the millimoles of carbon divide by the millimoles of oxygen. The millimoles of hydrogen divide by the millimoles of oxygen. The logic behind dividing by the smallest number is simply to ensure that our answers will all be bigger than 1. All right, if we divide by the smallest number, all of these answers are going to be bigger than 1. We won't have any decimal answers less than 1. It really doesn't matter, but it's a little bit easier for most people to deal with that. So the carbon was 5.52 millimoles, and the oxygen was 2.07. The hydrogen was 5.55, and the oxygen 2.07. So dividing 5.52 divided by 2.07, I get a number which at first is a little disconcerting, 2.66 repeating, so 2.67 I guess, millimoles of carbon for every 1 millimole of oxygen. That's not a nice number. Don't even think about rounding that off and calling it 3. That's not going to work. Dividing these two numbers, we get something similar, I think. 5.55 divided by 2.07, we get 2.68 millimoles of hydrogen for every 1 millimole of oxygen. Now, what do we do with those numbers? Those are really ugly numbers, aren't they? Well, not quite. Notice some basic decimals. If I take the number 1/2 and convert it to decimal, it's 0.5. If I take a number 1/3 and convert it to a decimal, it's 0.33 repeating. This was 0.66 repeating, and this is very close to 0.66 repeating. If I take 1/4, I get 0.25. 1/5, I get 0.2, etc., right? If I get a ratio that ends in 0.5, we got ratios that ended in 0.67. If I had a ratio that ends in 0.5, I could make it a whole number ratio by simply multiplying the top and bottom by 2. If I get a ratio that ends in 0.333 repeating, I could make it a whole number ratio by multiplying top and bottom by 3. If I get a ratio that ends in 0.25, I can make it a whole number ratio by multiplying top and bottom by 4, etc. Well, what do we do with 0.66 repeating? Well, notice that 0.66 repeating is simply 2/3 as a decimal. So again, if we want to convert it to a whole number ratio, we'll just multiply by 3, top and bottom. So I'm going to take that top ratio and multiply by 3/3. Notice I'm really multiplying by 1, so I'm not changing the ratio. I'll do the same thing on the bottom because it also has the 2.66, or 2.68, which is very close to 2.6 repeating. And I need, in the end, these denominators to have the same amount of oxygen, which they will in this situation. So 2.67 multiplied by 3 is 8.01. So what I end up getting is 8 moles of carbon for every, or millimoles of carbon, for every 3 millimoles of oxygen. So 2.67 times 3 is 8.01, which is 8, and 1 times 3 is 3. I also get multiplying on the bottom 8 millimoles of hydrogen for every 3 millimoles of oxygen. Now notice these two fractions have the same denominator, 3, and that's critical. If they didn't at this point, I'd have to make them the same. So if one of them was over 3 and the other one was over 2, then I'd have to make them both over 6, right? If one of them was over 4 and one was over 2, then I'd have to make them both over 4. I'd have to find a common denominator. So now we can say the empirical formula is C8, H8, and O3. There's the empirical formula of vanillin. But we were also asked to find the molecular formula. And to do that, we were told the molar mass of the vanillin was actually 152 grams per mole. The question told us that at the beginning. Notice that our empirical formula's mass is, let's calculate it, 8 times carbon, so 8 times 12 is 96, plus 8 times 1, the hydrogen, is another 8, so 96 plus 8 is 104, plus 3 times 16, the mass of oxygen, is 48, so 104 plus 48, our empirical formula's molar mass happens to be also 152. What we want to do is take the actual molar mass and divide by the empirical molar mass. In this case, we would have 152 divided by 152, so the actual molar mass divided by the empirical molar mass, and that gives us 1. Because it gives us 1, we know that these answers are the same. So therefore, the molecular formula of vanillin is the same as the empirical formula C8H8O3. If the answer to this ratio had been 2, then we would have doubled all of those subscripts. It would now be C16H16O6. If we'd had a ratio of 3, then we would triple the subscripts in our final answer. So because the ratio here was 1, the empirical and molecular formulas were the same. So you can see that a combustion analysis problem is a little bit more complicated conceptually and mathematically than the finding empirical formula using percent composition. But be sure you're familiar with both techniques for your test and exam.